Chapter 1.4, inverses of functions. And essential question, what is an inverse function? How do you know it's an inverse function? Very good. I'm going to go over this section of the book, and not every single bit of it. Like all books, this one has its pros and cons, so we're going to kind of roll with it. Okay, explorer. Recall that a relation is any pairing of the elements of one set, the domain, with the elements of the second set, the range. The elements of the domain are called inputs, while the elements of the range are called outputs. Function is a special type of relation that pairs every input with exactly one output. And so that a function would be something that passes what we call the vertical line test. In a one-to-one function, no output is ever used more than once in the function's pairings. In a many-one function, at least one output is used more than once. And so I'm going to give an example of that first paragraph of a one-to-one relation and a many-to-one. Okay, so we have a coordinate, we have a grid, okay, XY coordinate plane, and an example of a one-to-one function would be something like this, where a function is increasing for the entirety of its domain. This is going to be a one-to-one. So it's going to increase over the entirety of its domain, or decrease over the entirety of the domain. So I'm going to make a counter example here. So if we have this function here, which is going to be like the quadratic parent function. Okay, this is going to be what we would call a many to one. And the reason is because if we make the inverse of this function, the inverse of this function will not be a function. So one-to-one is where you are increasing or decreasing over its domain, and many-to-one is where we will change from increasing to decreasing, or from increasing to decreasing, and have some twists and turns. An inverse relation reverses the pairings of a relation. So that's another way of saying X and Y switch. That would be an inverse relation. If relation pairs an input X with output Y, the inverse relation pairs an input Y with that. So it's just another way of saying X's and Y's switch. The inverse of a function may or may not be another function. If the inverse function f of x is also a function, it's called an inverse function, and is written as this f negative 1 of x. And that's, this negative 1 is written like an exponent, but it's a notation for an inverse function. If the inverse of a function is not a function, then it is simply an inverse relation. So we're going to go over examples and show this principle in action. A, the mapping diagrams show a function and its inverse. Complete the diagram for the inverse of a function. Okay, so what we have here is, I'm going to get myself a skinnier pen. Okay, we have a function. Its a domain and respective range. Well, for x's and y's to switch, in this case, our input of 0 gives an output of -3. Well, for the inverse of that function, the x's and y's switch, so the output for an input of -3 is going to be 0. And then in the domain, we have a of a function, we have an input of 1, output of 2. Well, for its inverse, we have input of 2 becomes an output of 1. All right, so what we call this is a one-to-one. And if we drew a little graph of this, of the plot of the points, we would see kind of a more or less an increase as we go. Well, not exactly. We're going to sort of top off. But for these points themselves, they would be a one-to-one function. Is the inverse of the function also a function? Yes. Why is that? Because each input value has a unique output value. And I'm going to go ahead and look at, we're going to have a counter example here on the next page. So just stay tuned. Here we go. Okay, here we have another mapping diagram, is the function one-to-one. Well, here at the bottom, 1 can have an output of 2, or the input of 4 can have an output of 2. So if we take the inverse of that function, 2 can have an output value of 1 or 4. Now in this case, for the domain of 0, range of 3, well, the -3 will map to 0. But you see, we don't have a unique input, a unique output for every input. And so there is not, I'll say not one-to-one and why is that? There's not isn't a unique output for each input. Okay, so we have that. Is the inverse of a function also a function? No. Explain. Well, we can explain in terms of the vertical line test. The point whose coordinate pair is 2, 1 is going to be below, directly below the point 2, 4. So if we plot these points, we would have one point above another and would not be a function. And to graphically demonstrate what that looks like, I'm going to draw a little XY coordinate plane here. So the first point we have here is -2, -4. So here's -2, -4. So we have this point right here. We have -3, 0. So -3 over here, 0. That's another point. And then we have 2, 1. So we go to the right 2 and up 1. And then we put 2, 4 to the right 2 and up 4. So these points are above one another, and consequently this relation does not pass the vertical line test and is therefore not a function. Okay, the graph of the original function in step A is shown. Note the graph also shows the dashed line y equals x. Write the inverse of the function of set as ordered pairs and graph them. And so we're going to do that. We have the point -4, comma -2, where we're going to switch that to -2, comma -4. X's become y's, y's become x's. For the next one, we're going to have -3, comma 0. For the next one, we're going to have 2, comma 1. For the last one, we're going to have 1, comma 4. So we switched the order. And now it says graph them. So we're going to go here and put in, and you can see, can't you, the original points here? All these points already drawn are consistent with the original function. And now, I'm going to put it in blue since it's just the color coordinate. -2, comma -4. There's that one, -2, comma -4. -3, comma 0. 2, comma 1. And finally, the point 1, comma 4. So we go 1 to the right, up 4. What do you observe about the graphs of the function and its inverse in the relationship to the line y equals x? So here's the line y equals x, this diagonal line. Now, what I'm going to do is draw an arrow to demonstrate that we are reflecting about the line y equals x. This one comes down here, so I'm just drawing across that line y equals x. And I'll tell you what, I'm going to go ahead and get a skinnier pen, make a more detailed drawing. So here, this one will go over here, crossing the line y equals x. This one will come across here, across the line y equals x. This one here will go over here. And finally, this last point here will go down here. So we are crossing the line y equals x. So we have reflective symmetry about the line y equals x. What do you observe about the line? So the points reflect about line y equals x. Okay, so that's so far we've noticed that x's and y's switch places, and also the points will reflect about the line y equals x. Okay, next. D, the composition of two functions, f of x and g of x, written as f of g of x with the parentheses here, and this is the verbalizing of them. And this is a part in the book that really we haven't gone over compositions of functions yet, so we're going to weave this concept in as we go. I'm just going to skip through here. What is the relationship between the domain of a relation and its inverse? Well, the domains and ranges will switch places. I'm just going to write that. Domain of a function is the range of its inverse. And you notice I didn't say inverse function, because if we have the inverse of a function, we don't know, or unless we have to look and test to see if the inverse of a function is also a function. And if it's not a function, we call that the inverse of a function, a relation. Okay, we'll skip the discussion on the composition here. Explain one, finding the inverse of a linear function. Now here is something really you need to become aware of. This four-step process of converting a function into an inverse. And it says below, to check your work and verify that functions are inverses, we can find the compositions of these two functions are equal to x. And we haven't gone on the compositions yet. That's a four-step process. What I'm going to do as we go through these problems, I'm going to number these steps 1, 2, 3, and 4. Of course, that's what they have. You're going to see that as a notation. Okay, so here we have the function. We're going to take this function f of x equals 3x plus 4. Well, step 1 is going to replace f of x with y, so I'm going to call this step 1. Step 2 is what you do is, and I don't like this, the way to do this right now. I like to instead switch x and y. So the way I would do this is I would say, okay, I'd make this x and make this 3y here. And you just solve for y. And when you solve for y, so what they did is they solved for x. What you're going to do is you're going to divide by 3. So the way I would write this instead when you solve it, you'd say, okay, y, you're dividing by 3, equals x minus 4 divided by 3. And so that would be my step 2. Step 3 would be solve for y, the new y. And step 4, okay, solve for y. And step 4 would be to replace y, and that's the new y we solve for, with f negative 1 of x. And then we can compare these two, and then they do the verification of the compositions of functions below. I'm going to forego that right now. Anyway, let's go. We have the whole process here that they go through in the steps, and replace f of x with y. So you have y equals 2x minus 2, and you go through here, solve for x. X, you have y, you add 2 to both sides, so 2x equals y plus 2. Then you have y plus 2 over 2 equals x. And so interchange x and y. So what they do is they solve for x first. I like changing up here and solving. So you have y equals x plus 2 over 2. And so replace y with f negative 1 of x, so f negative 1 of x. And then we can find the inverse of the function. So this function here that I'm circling, f negative 1 of x, is the inverse of this original function. I'm arrowing over to. Okay, I don't reflect, I don't want to go over that right now. Find an inverse function. Okay, I want to demonstrate this one right here. F of x equals negative 2x plus 3. So I'm going to graph this function first. So negative 2x plus 3. We have a rise over run of negative 2 over 1. So we go down 2 over 1. So the function, the graph of the function is going to be this one right here. Okay, something like that. Now, we're going to go through the process. One, we're going to switch places with y. So I'm going to write this as y equals negative 2x plus 3. The second step I'm going to do is we're going to switch x and y. So I'm going to say x equals negative 2y plus 3. Then step 3, solve for y. So if we subtract 3 from both sides, we have negative 2y equals x minus 3. The last thing we're going to do is divide by negative 2. So y is equal to negative 1/2 x, and then this negative 3 divided by negative 2 is going to be plus 3 over 2. And then our final step is to replace y with f negative 1 of x. So we have f negative 1 of x equals negative 1/2 x plus 3/2. And now I'm going to go ahead and graph this, and we see if that's what we have. Okay, we look for the y-intercept, which is 3 over 2. Here it is. And we have negative 1/2 x, so that's negative 1 over 2. So we're going to go like this. So I'm just putting this in red right here. Okay. Now I hope you can make out that this blue line and this red line are reflections of each other about this line, this dashed line, y equals x. And so this relation of the reflection about the line y equals x is a graphical demonstration of an inverse of a function. And yes, when we are more comfortable with compositions of functions, we can go back and do a composition of these two functions and see if we end up with x. And if the composition of these two functions ends up as x, that's another indicator. Okay, modeling, real-world situations. Fortunately, inverse functions have a lot of real-world usage. And I don't want to go over any of these examples. Right now, we'll go over some of these or similar examples in class. So that's all I have for you today on this introduction to inverses of functions. Good luck, and thanks for viewing.